right, so please hand them to should have everyone's quiz. Right. So this is the answer to number 1, R-type, I-type, and J-type. Those are the 3 types of instructions. And then, man, you guys complicate this. All right. So then number 2, so these are the formats. You can expect to see this again on an exam. So number 2, recall I introduced this multiplexer problem here, 5.4. Remember this is the exact problem. You don't have to include all these gate costs, but those are the exact solutions here. I gave the exact same word-for-word problem. And then for the last problem, for some reason my page down is not cooperating today. I simply gave the exact same code from example 5.11. Exact same problem that we went over once and then spent 45 minutes going over a second time. So that's the exact same problem. So there's your answer key. Let's go review your notes. Let me make sure I'm recording. I am. All right, so last lecture we left off at direct map cache, right? And so we had this idea here where, just to go, this is an example of a direct map cache where we use the, the index and the tag, right? And so the whole idea is that we had one cache that's related to everything. So we're going to now have this, I use this concept of set associativity to try to break them down into sets to ultimately improve hit rate. And so a set associative cache starting at 6.17, so let me write up the, and this example question is 6.7. I know it says 5.7, it's 6.7. Set associative cache, we formally define it as a cache structure that has a fixed number of locations where each block can be placed. So what does this mean? Before, I had one block, but as you can see here, the way this is going to look, we actually have multiple blocks where I have an index and where I have an index and multiple tags, right? So what this means is instead of one cache, I'm using 2. This is known as a two-way set associative cache. So instead of when I break it down, I actually have normally if I had a 8 words, I would be breaking it down to an index of 3, right? I'm sorry, index of 3. But, so this would be 0, 0, 0 all the way through 1, 1, 1, right? And then we'd have a valid bit and then our memory, right? And the tag would represent which one we're substituting in. But here, it's two-way, which means the index is automatically going to be, we're going to cut this in half. So if we have 8 words and we have two-way, that means instead of using 3, we're going to use 2. And the difference would be, so if I had 8, I'm using 2 elements, and then I'm going to have an index of 2 because this multiplies it by 2. So if this was 16, each of these would be 8 elements in a two-way set associative cache. So now, here's the difference. I had a small set of problems in this example. So an n-way set associative. So if I had 32 words and a 4-way set associative. Right? So this would normally require 5 bits for 32. And so that would be our index. But I have 4-way, which means I can represent 1, 2, 3, 4, which means my index is actually only going to be 1 bit. So what can happen is when you max it when we substitute in, and this is going to be a good example because you're going to see over here we have multiple instances where the index is identical, but we use the difference in the tag to store 2. So normally, at the first, the issue is we're able to load more in. So if we start using these again, taking advantage of temporal locality, as we get more and more hits, its advantage over direct associativity is going to be significantly bigger because the hit rate is going to be improved. So let's go over example 6.7. So we're given a two-way set associative cache. On the exam, I'll expect you to draw these out. I'm going to have the next example where I say show me direct and show me set associative and compare the performance. So here I have set associative cache with 8 words, and here are the address references: 22, 26, 22, 26, 16, 3, 16, and 18. Show the sequence for accessing the cache. Assume the cache is initialized as empty. So that means all of our valid bits are no, and we have to go in here. So first, we break it up into index and tag, right? Each one. Tag and index, right? So here we have 1, 0. So if the way we did this, if we just, here, let me make this bigger. So we'll just get rid of all this here. There we go. Okay, so I have 22 as my first one, right? So how do we do this in direct? When we had 8, how do we split this up? Which one did we select? How do we choose which one we wanted to put in last class? Okay, so we had the tag, and the index was 3 bits, right? So it's a 1, 1, 0. So in this case, our index is only 2. So we go to 1, 0. And the first one, so we go to 1, 0, and we're going to put yes in the first one, and then the tag is going to be 1, 0, 1, and then data is going to be memory at that address, right? You see how that works? And then look at this, again, 26 happens to be the same index with a different tag. So normally this would be a swap if we had identical tags. But we have this second associative cache. So what we can do here is we go over here and we make this a yes, and then this becomes 1, 1, 0, and then memory of that element, right? So then next 2 steps are 22 and 26. So the reason I'm formulating the problem this way is because we would start getting a little bit of thrashing if we just kept using those same 2 memory elements. So instead, this now becomes 2 hits. And so now I can show you that we've gotten through these first 2 steps. Then 16 and 3, we go 0, 0, and you see 1, 0, 1. We have memory element of 16. Next step is 3 is 1, 1. So we go here. So you have 3. And now, this is where we get a little tricky. We go to 18. We have 1, 0 at the end here, right? So that's going to be our index. Now, how do we choose which one we want to swap out? Think of the idea of temporal and spatial locality. The one was not last year. For those of you who have taken algorithms or are familiar, what is that algorithm called that y'all just described? It's known as the least recently used algorithm, which is LRU. So basically, you just subtract the one that was least recently used. In this case, the one that happened to be least recently used was 22. So we swap that one out, which is why we have 18 there in the final solution. So then I have redrawn this here to show all everything. So does that make sense how we got here? So the whole goal for set associative cache is try to improve hit rate. So, any questions on this? Yes, Leo.
If we had 22, 26, 26, 22, you would swap the 26 in the second place?
Oh, no. Well, not, you're talking about least recently you got them?
Yeah.
Yes, we would. That's exactly right. That's a good question. So the question was, if we did 22, 26, 26, 22 here, and then we came around with 18, we would take out the 26 because it was least recently used.
So a hit is considered as used.
Yeah, a hit is if it's in there. So it's initially found to be empty. So we go in there, that's page miss. I'm sorry, cache miss, right? And so you go in there and you start filling it up, and after a while, if we had enough numbers in here, we get plenty full. And as you know from those of you who didn't know how to do the last problem, if you're constantly reusing the same registers and same data memory elements, eventually you're going to start having a lot of hits, which is why you can, when we have these example questions of like 95% for level 1, that's how we get there. So, but if we did it that way, yes, we would be swapping out the 22. Any other questions? All right, so example question 6.8 is where we're combining a bunch of concepts into one here. So this is going to be similar to what you'll see on your exam in a couple of weeks. 6.8, given a cache hierarchy with 8 words, so that's as much as I'm going to go on an exam, and a cache access time of 5 nanoseconds, and a memory access time of 20 nanoseconds, and the following set of memory accesses: 22, 28, 31, 22, 16, 13, 31, 8, 5, 13, 8, and 5. So A, if the cache is a direct map cache, so the sequence for accessing the cache and calculate the total time. So recall that we have, and then so part B is doing the same thing for set associative cache, and then calculate the improvement in performance. So those of you who thought thought they were done with performance questions, sorry, electrical engineers get to deal with it till you retire. So solution. So we have part one. Part one, figure out all the numbers in binary. You should be able to do that. So 22 is 1, 0, 1, 1, 0, all the way down through 5. So for sequence 1, for the direct associative cache, we have a miss, right? Because we assume that it's empty, just like we stated in the problem before. So then 22, 28. So 22 is going to be 1, 1, 0. It's going to go here, right? And then 1, 0, 0. So 28 is going to go there, right? So that's where we're going to start. So now 31 is going to go here. So we have a miss again. 22 is a hit because we already have it. 16 is a miss, so it's going to go here in 0, 0, 0 because of 0, 0, 0. 13 is a miss because 13 is 1, 0, 1. We go here, we don't have anything, so we load in 13. And now, when we go back up to our order, this is where things get interesting. So now we're up to 31, right? 13, 31's a hit. Now 8 happens to be the same index as 16, right? So that's why when you see in this final solution here, it's 8 because we have swapped out 16. So here I said 8 is a miss, overwrite 16. So 5 comes out. We have 13 in there. If you look, 13 and 5. So here's 13 and here's 5. They have the same value. So it's a miss, you overwrite 13. And then 13 comes back and you overwrite 5. 8 is a hit. And then 5 is a miss and overwrite 13. So this is actually, we got to calculate this out correctly. So that's 5 misses and 13 hits. So let me, there we go. So this is actually incorrect. So let's calculate this out. So if we have 9 misses and 3 hits in our cache access, every time the first thing we have to do is we have to go get to a cache, right? And if we miss, then we have to go to memory. So memory access time is 20 nanoseconds. So this is 3 times 5, going back to our equation from before, plus 9 times, and this becomes 20 plus 5, so that's 25. Right? That's going to be equal to 400. What's that?
440.
Oh, 440? Okay, so you're ready. 440? Wow. That can't be right. No, that's 8 times 25 is 200. That's 225 plus 15 is 240. Yeah. Okay, no, it's okay. There we go, 240. 240 nanoseconds. Does that make sense how I did that? All right, so that 195 is wrong. All right, so then part B, we're not going to do the same thing, except we're going to do set associative. So here you break it up into 2. And so when you have 8 words, what that means is, again, you're going to have 4. So 22, if I can, 22 is going to be a miss, right? Because as we started out before, now we're dealing, our indexes are 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, and 0, 1. And then these are your tags, right? So that means we're trying to use this dual set associativity to figure this out. So 22 is a miss, 28 is a miss, 31 is a miss. So 20, and so then now we get 22 is a hit, 16 was a miss, 13 was a miss. So 31 is a hit, 8 is a miss. So then in that case, now we have our least recently used. So what we've done here is we had multiple instances where we had 8, so 8 ends in 0, 0. So what happened is we had 16 was also in there, in 0, 0. And before that, we had 28. Right? So 28 was our least recently used because you see 28 came before 16. So that's different than 28 and 2 and 22, which we had before. Does that make sense? Like, I'm willing to draw this table up and kind of go through everything again over here on the side. So we had our dual set associativity. What's going on here is we have our index is 0, 0, 0, 1, 1, 0, and 1, 1, right? And so so we have valid, tag, and memory, and valid, tag, and memory. Right? So and our first hit was 22, right? So they're all no initially. So we go to 22. The 16 plus 4, or 16 plus 6, right? So that becomes 1, 0, 1, 1, 0, right? So 1, 0 is our initial value here. 1, 0, 1, 1, 0, so that's 22. So 22 never gets swapped out with anything. So we just put it here. So it becomes yes. And then it becomes 1, 0, 1. And then memory, we'll just put mem of 22 on the board here for shorthand. All right, so 28 is a miss. So that's 16 plus 8, right? So 16 plus 12. All right, so that becomes 1, 0. 16 is 1, 1. That's 16 plus 8 plus 4. 1, 1, 1, 0, 0. Yes. 1, 1, 1. And memory of 28. That's how it goes into 0, 0. So when 8 comes by, that's how we get the overwritten value here. So 31 is a miss. 31 is all 1. So we go yes. 1, 1, 1. Memory 31 here. So 22 we already have in there, it's a hit. 16 is a miss. So now 16 is 1, 0, 0, 0, 0. The index we use for set associativity is 0, 0. And then we go over here, so this becomes yes, 1, 0, 0, memory of 16. So 13 is a miss. So 13 is going to be 8 plus 5. So it's going to be 0, 1, 1, 0, 1. So it's going to be 0, 1, right? So there, here it is in 8. 0, 1, 1 is our tag, and then our indexes. So we go here, we go yes, and then 0, 1, 1, and then memory of 13. Okay. So then 13 becomes a hit. 8 is a miss. So by using least recently used, we know that 28 was used before 13. So getting rid of 28, we replace this with 0, 1, 0, and instead of 28, we have 8. So that becomes our cache there. And then 5 is a miss. So 5 is 0, 0, 1, 0, 1, 0, 0, 1, 0, 1. Wait, how did we put 0, 0, 1, 0, 1?
0.
No, 0, yeah. Am I having a brain fart here? That's 5, correct? Yeah. So that becomes 0, 0.
The tag is 0, 0, 1.
Oh, no, the tag is 0, 1. That's it. So then that becomes here, it goes yes, and then 0, 0, 1, memory of 5. And then that's where it is right there. And then from there we have 13 is a hit, 8 is a hit, and 5 is a hit. So that's how we're able to, this is where, as you can start seeing, this is where the benefit of a set associative cache comes into play. Because you'll start getting, you see how we have 1, 2, 3, 4, 5, 6 in there? So the only one we don't have in there is 28. Whereas with direct associative, we're actually swapping out a couple. And as a result, what you'll see is we actually had 7 hits as opposed to the previous one where we had 5 hits instead of 3 hits, right? So let's get rid of our incorrect answer that I have written up here and calculate a correct one on the board. This is wrong. It's not 165, but the ratio will probably be very similar. So we had, and just for, no, we had the previous one, we had 240, right? So we had 5 hits, so it's 5 times 5, so that's 5 times 5 nanoseconds, plus, and then you had 7 misses times 25, right? This is 25 nanoseconds plus 175. Yeah, so it's going to be 200. I was making sure I got the 175 right. So then your improvement in performance is what? Yes?
1.2.
But
1.2.
1.2 is not what was funny. These kids, how am I going to reach these kids? Okay, so that's 240 over 200 is our improvement in performance, right? So that becomes 1.2. So now you've completed the problem. Right? Any questions? So for the next 5 minutes, I want to just briefly talk about this idea of, no, let's start with virtual memory on next Tuesday. What was that example question? 6.8, so 6.3 to 6.8. And then, did we cover any other TGOs? No, wow, you guys have it. Yep. So, there you go, there's your, you survived the quiz. There's an easy TGO assignment.